Hello everyone. In this video, we'll be learning about the electromagnetic waves. Before we dive deeper into the concept, let me ask you four brilliant questions. Question number 1. Under the high tension power line, the fluorescent light glows faintly. Can you explain this? The physicist Richard Box installed more than 1300 fluorescent lights in a field under the high tension power line, and you can see the mesmerizing result. This result can be explained using the concepts of the electromagnetic waves. If you have any idea about it, let me know in the comment box. Here comes the second question. The air traffic controllers use the radars to determine the distance of a plane, the shape or size of the plane. How this is achieved? If you have any thought about this, let me know in the comment box. Then there comes the third question. In United Kingdom or in many other European countries, to watch a television, you need a license. In UK especially, without the license, they impose a fine of more than 1000 British pounds. Okay. So how the authorities come to know about unlicensed use of the television? Any thought, any idea? Let me know. And then comes the last fourth question. NASA engineers are building up a prototype of a solar sail. This spacecraft will be moving in the vast space using the radiation pressure caused by the sun. Now, the material chosen for this kind of spacecraft should be highly reflective or highly absorptive. What is your thought? What is your idea? Post your opinion, your answer in the comment box, and we'll explore all these beautiful answers during this video. So let's begin this beautiful journey. First of all, we will see the source of the electromagnetic waves. Then we will see the properties of the electromagnetic waves, and we'll be taking up numerous great questions over these properties. And at the end of the video, you'll get a checkpoint for the conceptual practice, and you'll be getting the answers of all these checkpoint questions. Got it? Now, let's look at the sources of the electromagnetic waves. According to Maxwell's theory, any accelerated charge will radiate the electromagnetic waves. Okay. For example, an oscillating charge, it will radiate the electromagnetic waves. Your mobile phone radiates the electromagnetic waves. It also receives the electromagnetic waves. The current in our house, the alternating current, the charges are oscillating in the wires. So they will also radiate the electromagnetic waves. So the concept is simple. Accelerated charges are the source of the electromagnetic waves. Let's observe the properties of the electromagnetic waves. The frequency of the electromagnetic waves is equal to the frequency of the oscillation of the charge. For example, if a charge is oscillating with the frequency 10 to power 15 Hertz, then the produced electromagnetic wave will also have the frequency of 10 to power 15 Hertz. Okay. Another important thing, the energy of the electromagnetic wave comes at the expense of the energy of the source, means the accelerated charge. Actually, some part of the energy of the accelerated charge gets converted to the electromagnetic wave. Here on the screen, you can see a picturization of the linearly polarized electromagnetic wave. Actually, humans can never see the electromagnetic waves. To have the idea of the things, we are using this picture. Okay. And by the word linearly polarized, what do you mean? Linearly polarized means the oscillations of the electric field are confined along a particular axis, such as in this diagram. If you observe very carefully, the sinusoidal oscillations of the electric field are confined along the y-axis only. This kind of wave is known as linearly polarized. Got it? Now, in this diagram, there is another important thing. The electric field, which is indicated with the blue color, the magnetic field, which is indicated with the red color, they are perpendicular to each other. E vector is perpendicular to B vector. And the direction of the propagation of the electromagnetic wave is perpendicular to both. Electromagnetic wave is propagating along the x direction, which is perpendicular to the y direction as well as perpendicular to the z direction. I am explaining the things again. In an electromagnetic wave, the direction of the electric field, the direction of the magnetic field, and the direction of the propagation of the electromagnetic wave, all three are always mutually perpendicular. And eventually, we can use the right hand rule to determine the direction of the propagation of the electromagnetic wave. How? You stretch your right hand fingers along the electric field, the blue vector, then curl them toward the magnetic field. Your right hand thumb will point in the direction of the propagation of the electromagnetic wave. E cross B gives you the direction of the propagation of the electromagnetic wave. You get this? Keep in mind, in an electromagnetic wave, the E vector, the B vector, and the direction of the propagation of the electromagnetic wave will always be perpendicular. That's why the electromagnetic wave is a transverse wave. To give you the better idea, I am giving you an example. Suppose this is indicating the oscillation of the electric field. This indicates the oscillation of the magnetic field, and direction of the motion, my motion, is the direction of the propagation of the electromagnetic wave. Then how things will take place? The electric field and magnetic field, they are oscillating and the wave is moving in the forward direction. I am explaining it again. Electric field oscillations are in the vertical direction, magnetic field oscillations are perpendicular to that, and even the wave will propagate perpendicular to both the oscillations. E vector, B vector, and the direction of propagation of wave. Watch it carefully. Okay, I hope you got the idea. So now we'll write few formulas and the interesting things we can observe. Suppose I write the expression of the electric field. Since electric field oscillations are confined along the y-axis, I indicate it as Ey is equal to E naught sine of kx minus omega t. What is E naught here? It is the amplitude of the strength of the electric field. What is k here? K is the magnitude of the propagation vector or the wave vector. This k is equal to 2 pi by lambda. Okay. The propagation vector or wave vector is always directed along the direction of the motion of the wave. Okay, direction of the propagation of the wave. And omega is equal to 2 pi f, where f is the frequency. You get it? Then we write the expression of the strength of the magnetic field, which will be Bz. It is equal to B naught sine of kx minus omega t. You observe one thing in these two expressions. These two expressions are in same phase. Okay. So in an electromagnetic wave, the electric field and the magnetic field will always be in the same phase. It means the moment the electric field strength is 0, the magnetic field strength will also become 0. The moment electric field strength reaches to its peak value, the magnetic field strength will also reach to its peak value. The moment electric field strength becomes E naught by 2, at the same moment, the magnetic field strength will also become B naught by 2. In an electromagnetic wave, the electric field and the magnetic field are always in the same phase. Okay. Another important thing, if we divide E and B, we will be getting the speed of light in the vacuum C, which is equal to 1 by root of mu naught epsilon naught. Another interesting expression. Okay, even if you divide E naught and B naught, the amplitudes of these two fields, you will get the same result, because when you divide E and B, this sine and sine term will get cancelled out, so ultimately you will get the same result. This data comes out to be 299,792,458 meter per second. This is the speed of light in vacuum. The electromagnetic waves travel with this speed in the vacuum. Okay, it was obtained by the great genius Maxwell. Now, all electromagnetic waves will travel with the same speed in the vacuum. Whether you take X-ray, you take the gamma ray, you take the light, you take the microwave, they all will be traveling with the same speed in the vacuum. For example, if I ask you, there is a laser light, red color. There is another laser source, the blue color light. Now, these two light rays are traveling in vacuum. Which will travel faster? Your answer should be both will be traveling with the same speed, 299,792,458 meter per second. Okay, irrespective of their frequencies, irrespective of their wavelengths, all electromagnetic waves will travel with same speed in the vacuum. Let us write another important point. Since the propagation vector is perpendicular to the electric field as well as perpendicular to the magnetic field, it means what I can write, E vector dot k cap should be equal to 0. B vector dot k cap should also be 0. Okay, the reason was simple. E vector was perpendicular to k vector, B vector was also perpendicular to k vector, and the dot product of two perpendicular vector becomes 0. You should note down these informations. I'll clear up the things here and then we'll proceed for the further properties of the electromagnetic waves. Let's look at the next property. The speed of the electromagnetic wave in a medium is given by this formula. You know the values of the mu and the epsilon. You can write them as mu naught, mu r, epsilon naught and epsilon r. Okay, what is mu naught? Permeability of the vacuum. What is mu r? Relative permeability of the medium. What is epsilon naught? Permittivity of the vacuum or the free space. And what is epsilon r? Relative permittivity of the medium. Done. So if I divide these two things, C and V, will obtain the expression for the refractive index that will be used in the chapter Geometric Optics. C by V, and when you do the computation, it comes out to be mu r epsilon r. And the most important thing here will be plus and minus sign. It comes from the Maxwell's theory. We are not going into the detail. The refractive index of a medium can be negative. If you have not heard about this, you will see the details in the videos of the geometric optics. At this point of time, you should just note it down that refractive index of a material, of a medium, can be negative. Such materials are known as the metamaterials. Usual positive refractive index you have already seen, such as normally the refractive index of the glass is 1.5. So that data is positive. And this formula gives you another interesting insight, that the speed of the propagation of the electromagnetic wave depends upon the electric and the magnetic properties of the material. Okay, for example, light is an electromagnetic wave. Now its speed will be different in the different material. Light, the electromagnetic wave, has the maximum speed in the vacuum. In the glass, the speed of the light will be less as compared to its speed in the vacuum. Got it? Note it down, then we'll go further. Next important point, all electromagnetic waves carries the energy and the momentum. For example, the life on the earth exists because of the energy coming from the sun in the form of the electromagnetic waves. This statement is pretty powerful. We people exist because we receive the energy from the sun in the form of electromagnetic waves. This will give you the idea about the importance of this topic, the electromagnetic waves. Okay. Next important point, the electromagnetic waves are electrically neutral. It means there is no charge on the electromagnetic wave and they remain unaffected by the external electric and magnetic field. Pay attention. Suppose an electromagnetic wave is propagating in this direction, and then suddenly you switch on some external electric field or some magnetic field. Whatever you do, it won't hamper the propagation of this electromagnetic wave. It will continue along its original path. It's an important thing. For example, suppose there is a capacitor which is fully charged. So on this plate there is positive charge, on this plate let's say there is negative charge, and there is electric field in between them. Okay. Now some X-ray is sent here. What will happen to this X-ray? It will deflect upward, it will deflect downward, or it will continue straight. What is your opinion? Answer is simple. Since X-ray is an electromagnetic wave, it remains unaffected by the electric field or magnetic field. It will continue straight along its original path. Now suppose you set up some magnetic field here in this space into the plane of the board in this direction. Okay, what will happen to the path of this X-ray? Even in the presence of this magnetic field, this X-ray will keep on moving along its original direction of propagation. Okay, keep in mind the electromagnetic waves remains unaffected by the external electric and the magnetic fields. Another practical example I can give you. Suppose you have two laser lights. One is of the red color, other is of the blue color. You switch on the red laser light, then you see a beam in this direction. Then you switch on the blue laser light, you get the other beam. These two beams will keep on moving independent of each other. Now suppose sometimes you switch on the red beam, sometimes you switch off the red laser. It won't hamper the motion of the blue light. Getting my idea? What I am trying to say, when you keep on switching on or off the red laser, here the electric field due to the red laser sometimes will be present, sometimes will be absent, but it won't hamper the motion of the blue light. I hope you understand this thing. These concepts will be using extensively in the chapter Geometric Optics or many other chapters. So you should note it down, then we'll go further. Let me ask you a brilliant question. On my hand, the EM waves, the light is reaching. This light will exert the force on my hand. Do you agree? Although that force will be very tiny, in few numerical questions I'll prove that force will be negligible. But conceptually, if I ask you that force on my hand is due to the electric component of the EM wave, is due to the magnetic component of the EM wave, or is due to both, what you will reply? It's a brilliant question. Electromagnetic waves exert the force on the surface. That force is because of the electric field component, is because of the magnetic field component, or both. Pause the video here, think about it and then post your opinion in comment box. Then we'll be discussing the correct answer. Don't just go forward. I am waiting for your opinion in comment box. Okay, I hope you have written your opinion in the comment box. The correct answer is force on the surface due to the electromagnetic wave is because of the magnetic field component. How many of you thought the correct answer? Brilliant. I'm explaining the things here. Suppose here is a surface, okay, and for simplicity I'm showing the surface like this. We consider some electron at the surface. EM wave is traveling in this direction. Done. In EM wave I'm showing at some moment the electric field is like this, and at that moment the magnetic field is perpendicular in this direction. I cannot draw the three-dimensional diagram on the 2D board, so that magnetic field I am showing like this. I hope you understand the things. Now, when this EM wave reaches at this location, the electric field will be like this. Okay. This electric field will exert a force on the electron in which direction? In the downward direction. I hope you understand that thing, because the formula for the electric force we already know. F electric is equal to Q times E vector. Here Q is negative, so the electric force will be in the opposite direction of the electric field. Due to this electric force, electron will start moving in this direction, so the velocity vector will be in this direction. Do you agree? Now let's think about the magnetic force. What is the formula for the magnetic force on a moving charged particle? F magnetic is equal to Q V cross B. That also we know. So V vector is in this direction and B vector is coming out like this. Try to use the right hand rule. Q V cross B. V is in this direction, B is like this. What is your opinion? Do it quick. Where is the magnetic force? Correct. Think about it. V is in this direction, B is in outward direction. So Q V cross B, if you want to do, you will obtain first V cross B, which will be pointing like this. Then you put the value of Q, which is negative. So this should be the correct direction. It means the magnetic force will be in this direction. Do you agree? This magnetic force creates the radiation pressure on the surface. So it's an important answer. In an EM wave, the magnetic component is responsible for creating the radiation pressure. Let's try it again. We know that electric and magnetic fields are oscillating. After some time, let's say the electric field is in this direction, the downward direction, and the magnetic field is in this direction. Actually, magnetic field is inward. I cannot show that, so I have shown it like this. Okay. Now we try the things again. Electric field is in downward direction. So the electric force will be in which direction? We know that electric force will be in upward direction. Okay. Due to this electric force, electron will gain a velocity in this direction, let's say. Done. Now do the QV cross B. B this time is inwards like this. First of all, let us try to obtain V cross B. Where is V? In this direction. Where is B? In this inward direction. So V cross B, thumb is pointing like this, but Q is negative. When you put that negative Q here, the direction of the magnetic force is in the same as the previous one. So think about this. The electric force will keep on oscillating. Electric force will increase as the strength of the electric field increases. then electric force will change its direction. In one cycle, the electric force will be zero on an average. Why? Electric field strength will increase itself. Electric field strength will decrease. Electric field will change its direction. And in one cycle, if you check carefully, the average electric force is zero. But in one cycle, the average magnetic force is non-zero. So it is the magnetic force which causes the radiation pressure. This electric and magnetic component both are delivering the energy to the surface. Done? You may note it down. Then we'll see the next property of the electromagnetic waves. Next important thing for the EM wave is the knowledge of the Poynting vector. It was proposed by the British physicist John Henry Poynting in 1884. The Poynting vector, S vector, is defined as 1 by mu naught E vector cross B vector. The magnitude of the Poynting vector gives us the intensity of the EM wave. It is also known by the name power flux or the radiant flux density. And the direction of the Poynting vector is always in the direction of the electromagnetic waves propagation. For example, suppose the electric field is in the upward direction like this. The magnetic field is coming towards you in this direction. Then the Poynting vector will be in this direction, the S vector. S vector will always be in the direction of the propagation of the EM wave. We can check E vector cross B vector is pointing in this direction. So S vector is in the direction of the propagation of EM wave. Okay, you may note down these things. Now we are going to derive few familiar expressions for the intensity, and will use the magnitude of the Poynting vector for that. So let's begin. We know that magnitude of Poynting vector is written as EB by mu naught. Okay. And the strength of the electric field was given by E naught sine kx minus omega t. And the strength of the magnetic field was given by B naught sine of kx minus omega t. I hope you remember these things. Now I am submitting these values here. So the S comes out to be E naught sine kx minus omega t, B naught sine kx minus omega t divided by mu naught. Okay. S can be further written as E naught B naught by mu naught sine square kx minus omega t. Suppose we want the average value of this S. It can be written as average intensity also. I average will be equal to E naught B naught by mu naught, and we require the average value of this expression. Do you remember what is the average value of sine square theta? In the mathematical tools playlist, there is a video. You'll get that value of sine square theta average for one complete cycle is equal to 1 by 2. So here I am putting up the average value of the sine square function. Okay. Now this in turn can be written as half epsilon naught E naught square into C, or this can be written as B naught square by 2 mu naught into C. How to obtain these expressions? Just pay attention. I am simplifying this expression again. We know two values. So here I am doing the replacement. See, E naught at the place of B naught, what we can bring? E naught by C. Do you agree? There is mu naught here, there is 2 here. Done. Now I am multiplying C here, dividing the C here. This is c square. What will be the value of c square from here? 1 by mu naught epsilon naught. So this can be simplified further. Mu naught is getting cancelled out. What you are left with? This expression. Done. Now in this expression, you replace the value of E naught as C times B naught. At the place of E naught, put C times B naught and you'll be getting up this expression. So the calculations are simple. If you need the magnitude of the Poynting vector, you can use this formula, and this magnitude is technically equal to the intensity. Average intensity will be given by these expressions. I recommend you to learn these formulas. Mainly in the questions we'll be using these formulas, and generally in the questions you will find the word intensity. Whenever in the question there is a term intensity, we should think about the average intensity. Actually, the electric field and magnetic field both are oscillating, and they are oscillating at rapid pace. So generally we'll take up the average values only. If you need intensity at a particular moment of time, then you should put here that value of time, you should put the value of x, and then you'll get the intensity at a particular moment of time. Another important thing, this average intensity is also equal to the average value of the radiant flux density in one cycle, or this average intensity is also equal to the average value of the power flux in one complete cycle. Got it? You may note down these informations and then we'll proceed further. Now we'll derive a mathematical expression for the energy density of an EM wave. So let's see it here. The energy density of EM wave will be actually summation of the electric energy density and the magnetic energy density. In EM wave, both electric and magnetic fields are oscillating simultaneously. So sum up these two energy densities and you'll get the energy density for the EM wave. Okay. Formula for the electric energy density, I hope you remember from the electrostatics. It was half epsilon naught E square. And formula for the magnetic energy density in the chapter magnetism, you might have seen this. Okay. I'll be putting up the values. As usual, our E was E naught sine of kx minus omega t, and the B was B naught sine of kx minus omega t. Okay. So going further, putting up the values, epsilon naught by 2 E naught square sine square kx minus omega t plus B naught square sine square kx minus omega t divided by 2 mu naught. Do you agree? This sine square kx minus omega t is present in both terms, so it can be taken common. Expression will look like epsilon naught by 2 E naught square plus B naught square by 2 mu naught, and here we are left with sine square kx minus omega t. Okay. This is the expression for the energy density at any x and at any time t. Fine. Now the sine square theta can be written as 1 minus cos 2 theta by 2 trigonometry. I hope you remember this formula. So I'm doing the replacement here. Epsilon naught by 2 E naught square plus B naught square by 2 mu naught, and here comes 1 minus cos of, this factor is pretty important, 2 kx minus omega t by 2. Here comes one powerful statement. In an electromagnetic wave, if the electric and magnetic fields oscillate with frequency f, because we know the value of omega. Omega can be written equal to 2 pi f. So both electric and magnetic fields are oscillating at the same rate with the same frequency f. Then the energy density will oscillate with what frequency? Pause the video here and type your answer in the comment box. In an EM wave, if electric and magnetic fields are oscillating with the frequency f, then the energy density of that EM wave will oscillate with what frequency? The answer is 2f. Here actually 2 is getting multiplied. I hope you understand this thing. Here will be 2 omega. So there will be 2 into 2 pi f. So the energy density will oscillate at a rate of 2f. It's important thing. It might asked as a question in the examination. Okay. So you should note it down up to here. Then from this expression of the energy density will derive the average energy density, because electric field and magnetic fields are oscillating and they are oscillating at a rapid pace. So usually will be using the average value of the energy density. That I'll do on the next screen. You note down the things up to here. Here we have the expression of the energy density, and to take the average of that expression, we have to take the average of the sine square function, because this epsilon naught, E naught, 2, B naught, mu naught, everything is constant. So if you wish the average of this function, you need to take the average of the sine square function. And in trigonometry, we have already seen for a complete cycle, the average value of the sine square function comes out 1 by 2. So the average energy density will be epsilon naught by 2 E naught square plus B naught square by 2 mu naught multiplied with 1 by 2. From where this 1 by 2 is appearing? I am taking the average value of the sine square function. Okay, that is 1 by 2. We can simplify it further. Here is another interesting insight. If we look at this formula, the amplitude of the electric field is much greater than the amplitude of the magnetic field. What I mean to say, E naught is much greater as compared to B naught. Okay. So few people think that the electric energy density will be more as compared to the magnetic energy density, but that's a misconception. The truth is, the average value of the electric energy density and the average value of the magnetic energy density, these will be equal. Keep in mind, for an electromagnetic wave, if you take the average of the electric energy density as well as the magnetic energy density, they will come out to be same. So you should note down these informations and then we will proceed further. If you require, I'll derive the things. I'll prove that average energy density for the electric field and the average energy density for magnetic field are equal. You note it down up to here. I'm going to prove that for an electromagnetic wave, the average electric energy density is equal to the average magnetic energy density. Pay attention. What is the value of average electric energy density here? 1 by 4. 2 and this 2 will make 4. Epsilon naught E naught square. And what is the value of the average magnetic energy density? It is equal to B naught square by 4 mu naught. Do you agree? We have to prove that these two parameters are equal. Computation is simple. We'll be utilizing these things again. For example, I am doing the replacement here. At the place of E naught, I can bring C times B naught. Check it. 1 by 4 epsilon naught C square B naught square. And C square can be written as 1 by mu naught epsilon naught. I hope you agree with this thing. Now check it. Epsilon naught is getting cancelled out, and these two parameters are equal. So again, I am repeating it because it's pretty important. Although the amplitude of the electric field is much greater as compared to the amplitude of the magnetic field, the average energy density of the electric field and the average energy density of the magnetic field are actually equal for EM wave. Suppose someone asks you what is the ratio of the average electric energy density and the average magnetic energy density for EM wave, then what should be your answer? 1. They are equal. Light is falling on my hand, EM waves, the radiations are falling on my hand. Then the electric field and the magnetic field of those electromagnetic radiations, they are actually delivering equal amount of energy to my hand. Done? So this is the important piece of information. You should note it down and then we'll proceed further. Now we'll discuss few more important properties of the electromagnetic waves. The EM waves can be reflected, can be refracted, can be polarized, can be diffracted, shows the interference. There are numerous properties which will be taught in the different videos. Done? The EM waves carries the energy and the momentum. For example, life on the earth exists because the electromagnetic waves coming from the sun carries energy to the earth. This is pretty powerful statement. We people exist because we receive the energy from the sun in the form of electromagnetic waves. Got it? Another important concept. Suppose the electromagnetic waves having energy U are incident perpendicular on a surface and they are completely absorbed. Then they will deliver the momentum U by C to the surface. Here U is the energy of the EM waves and C is the speed of light in vacuum. Okay. Another important concept. If the EM waves are incident perpendicular on a surface and reflected 100%, then these will deliver the momentum 2U by C to the surface. We'll be exploring these concepts using the questions. You'll get the better idea. Note it down. Here is the first question, simple formula based question. So I urge you, pause the video here, write the formulas and try to obtain the answers yourself. Then later on you can match the answers with the board. Okay, give it a try. I hope you are done with your calculations. The calculations are pretty simple. So I'm starting the solution here. First part, we require the amplitude of the electric field. If we pay attention to the equation, we can directly say that E naught is equal to 3.1 Newton per coulomb. Okay. Second part is asking us for B naught, the amplitude of the magnetic field. For that, we remember a relation. E naught by B naught is equal to C. So B naught will be equal to what? E naught by C. Simple calculation and we'll get the answer. The third part is asking us for the lambda. We already know that K is equal to 2 pi by lambda. What is this K? The magnitude of the propagation vector or wave vector. The K is given to us as 1.8. All the data is in SI units. So when we write the final answer, we should be using the SI units. This computation will provide us the value of lambda. Okay. Now, after getting the lambda, question is asking us about the direction of the propagation of EM wave. That answer will be minus j cap. Why? Just pay attention. If we compare the format, it is like as E naught sine of ky plus omega t. Compare it with the given format E naught sine ky plus omega t. If all the sign here in bracket are same, this sign here is positive, okay, and the sign here is also positive, then wave will always travel in negative direction. The details of this concept are available in the string waves chapter. There will be the separate video on that. Right now you just learn the concept that if all the signs in this bracket are same, then the wave will be traveling in the negative direction. And since here we are talking for the y coordinate, so we'll be using the j cap but with a negative sign. Got it? Suppose the same equation was given like this: E naught sine minus ky minus omega t. Can you tell the wave is propagating in which direction? All the sign here are same, then the wave will be propagating in the direction of minus j cap. Y means j cap, okay, and all the sign here are same, so here should be a negative sign. Another idea, suppose I give you an expression like this: E naught sine of ky, here is a negative sign and here is a positive sign like this. Now the wave is propagating in which direction? Any guess? In this case, the wave will be propagating in the positive j cap. Here the sign are opposite. When the sign are opposite, wave will propagate in the positive direction, and y means we have to take up j cap. For this case, we have to consider the positive j cap direction. Another possibility, suppose E is equal to E naught cos, sine cos, there could be anything, it's not an issue, kz minus omega t. Then the wave will propagate in which direction? Pause the video here and post your opinion in comment box. It's simple thing, the sign here are opposite in this bracket. Damn sure the wave must propagate in the positive direction. Whenever the sign here are opposite, wave propagates in the positive direction. Now positive direction of what? Positive direction of z. It means k cap. This k cap is a unit vector along the z axis. Keep in mind, don't get confused. This k represents the magnitude of the wave vector, and this k cap represents a unit vector along the positive z axis. Okay, do not intermix them. So we are done with the fourth part. Then I am going further for the fifth part. In fifth part, we require the average electric energy density. You remember any formula for the average electric energy density? Simple formula based question. Average electric energy density is equal to 1 by 4 epsilon naught E naught square. Rest all is mathematics. We know the value of epsilon naught, we know the value of E naught. Now we require the average magnetic energy density. I hope you can do the calculations yourself. Actually, average magnetic energy density will come out to be same, but I am writing the formula B naught square by 4 mu naught. You can do the calculations and you'll get the answer. Now, the next part is asking the average energy density of the EM wave. For that, we will sum up these two answers. Okay. I hope you have noted down all the previous solutions. So I am proceeding further for the remaining answer. In next part, we require the frequency. Frequency can be written as omega by 2 pi. I hope you remember the formula. Omega was equal to 2 pi into f. So we know the value of omega, we know the value of 2 pi. Put up the values, we'll get the frequency. In next part, we require the average intensity. You remember any formula for the average intensity? average intensity was equal to half epsilon naught E naught square into C, or there was another formula, half B naught square C by mu naught. In any of these formulas, you put up the values. We know epsilon naught, E naught, B naught, everything. C is the speed of light in vacuum. Another part of the question is asking the average intensity due to electric field. That's important. Due to electric field, actually the average intensity will be equal to half of this total intensity. So I by 2 will be our answer. Next part is asking average intensity due to magnetic field. Due to magnetic field, the contribution is also half. So actually in the average intensity of EM wave, there is half contribution because of the electric field and there is half contribution because of the magnetic field. Pretty important thing. Now solving the last and the most important part of this question, the expression of B vector. We know that it will be written as B naught sine of ky plus omega t. We already know the value of omega, we know the value of k, we know the value of B naught from the previous calculations. All we need to obtain the direction in which the magnetic field is varying sinusoidally. So that direction will be actually k cap. How? Suppose this is I cap, this is j cap, and this is k cap. The electric field vectors are varying sinusoidally along the I cap, so E vector is in this direction. Suppose I take up the B vector along the k cap. You check the direction of E vector cross B vector. It's pointing where? Stretch your right hand fingers along the E vector and then curl them toward B vector. The B vector is actually coming out of the board. So stretching right hand fingers along E vector and curling them toward B vector, thumb is pointing down. And actually the down direction is minus j cap. And if we look at this expression, the velocity of wave was along the minus j cap only. Check it. All the sign here are positive. So the velocity of wave, if you check, is along minus j cap. Y means j cap and all here sign are positive. So we put here a negative. Okay. Now the calculation is pretty simple. We put up the values and we get the expression for the strength of the magnetic field vector. So this was a nice question. Almost every formula got covered. I hope you all got the correct answer. Note it down. Then we'll take up the next good question. Here is the second question and it's a simple one. Only one option is correct. So if you wish, you may pause the video here and you can give it a try. Then we'll discuss the correct option. I hope you have chosen the correct option, which is the second option. How? Let's pay attention for the solution. We know the expression of the electric field associated with the incident EM wave, that is given as E naught I cap cos of kz minus omega t. If we pay attention to these parameters, we can easily determine the direction of the propagation of the wave. See here, z is present. It means the EM wave should be traveling along the z axis. Now positive z or negative z, that will be decided by looking at the sign here. This is positive, this is negative. Many times in this video we had the talk, when the sign here are opposite, then the wave travels along the positive direction. The incident electric field oscillates along which direction? Do you get this? Now we have to choose a correct option for the electric field associated with the reflected wave. See, If this is the wall and here is the incident electromagnetic wave, then how will be the reflected wave? It will be moving in this direction. Do you agree? This is the reflected electromagnetic wave. So actually it will be traveling along the same line. Just for the sake of the simplicity, I am showing it displaced a little bit. Okay. If incident light is like this, the reflected light will be in the opposite direction. Now this direction has been chosen as plus z, then this direction will be the minus z. For reflected wave, if I choose the correct option, why E naught I cap? There is a word in the question, if you pay attention, this is optically inactive material. Optically inactive material means it will not rotate the plane of the polarization of the EM wave. Actually, this electromagnetic wave is linearly polarized. Why? The oscillations of electric field are confined along a single line, along a single axis. Got it? If this is a linearly polarized electromagnetic wave and this material is optically inactive, it means the reflected wave electric field will have the same state of the polarization. So it will remain E naught I cap only. Then cos of kz plus omega t. Why so? We know that the reflected EM wave travels along the negative z direction. How you will decide that? Z is present here and both sign here are same. It means the reflected EM wave travels along minus z. Do you get this? Here is the z coordinate, so it should travel along the z, but here the sign are same, both are positive, so it should travel along the negative z axis. If you have any doubt how this is happening, it will get better and more clarified in the video of the waves on the string. There lies a derivation how the pulse travels on the string. If you understand that derivation very well, then this part is pretty easy for you. Okay. So this is all about this question. The incident EM wave was traveling along the positive z direction. Looking at this bracket, we get the idea. The reflected one is traveling along the negative z direction. But in the incident as well as in the reflected electromagnetic wave, the oscillations of the electric field will be in the same direction because this material is optically inactive. So the state of the polarization of this EM wave will remain unchanged. Okay. Simple and easy question. You may note it down, then we'll go further. Here is a brilliant question. More than one choices are correct. So you take up your time and try to choose all the correct options. Then we'll be simplifying things on the board. I hope you have chosen the correct options, which are the first option, the third option and the fourth option. I am simplifying the things on the board. Pay attention. We are given an expression of the electric field. E is equal to E1 I cap minus E2 J cap cos of kz minus omega t. Look at this part. It will give us the idea in which direction the EM wave is propagating. Since here is z present, so the EM wave must travel along either positive z or negative z. We have to choose anyone in between them. Among these two options, how we will clarify? Look at the sign here. Here is plus, here is minus. There are opposite sign. When there are opposite sign, then the pulse will travel along the positive z. Another piece of information from this, if we look at the direction of the E vector, this direction is along a specific line. It means it is linearly polarized field. This electric field is linearly polarized. What does it mean? The oscillations of electric field are restricted along a single line only. Got it? Now, we need the expression for the associated magnetic field for this EM wave. So, B vector should be equal to 1 by C of E2 I cap plus E1 J cap cos of kz minus omega t. We remember in EM wave the E and B are in the same phase, so you can check here the phase is same. This also indicates that EM wave is propagating along plus z. Now why I have chosen only this expression for B? I have few tests. Through them we can be sure that this is the correct expression of B. Number one, we know one formula that E naught by B naught is always equal to C. Do you remember? E naught is the amplitude of the electric field, B naught is the amplitude of the magnetic field. So from this part we can obtain the B naught. From this part we can obtain the E naught. I am putting up the values. The E naught will be root of E1 square plus of minus E2 square. Do you agree? You know how to take the magnitude of the vectors. Now let's obtain the B naught from here. It will be root of 1 by C square, and then inside the bracket we have E2 square plus E1 square. Check it. In RHS we are actually getting C. Okay, it means first test is getting satisfied. I have another test for this. Since in an EM wave electric field and magnetic field are always perpendicular to each other, we already know EM waves are transverse in nature, so I can write that E vector is perpendicular to B vector. Therefore E vector dot B vector, let me know what should be the result. Two vectors are perpendicular to each other, orthogonal vectors. Their dot product is 0. It means E vector dot B vector should come out 0. I'm going to check this thing, and just for saving the time I'll do the dot product of these parts, these vectors. So let's check it here. E1 I cap dot E2 I cap. I'm writing the data here. E1 I cap dot E2 I cap. Then dot product with this E1 I cap dot E1 J cap. Then dot product of these two vectors, minus sign because of this, minus of E2 J cap dot of E2 I cap. Then dot product of these two vectors, minus into plus, so here will be a negative sign. Let us simplify it further. I cap dot I cap becomes 1. Okay, so here we are left with E1 E2. I cap dot J cap becomes 0, so plus 0, no need of actually writing that. And then J cap dot I cap also becomes 0. Here is a negative sign, and then J cap dot J cap becomes 1. So we are left with E2 E1. E1 E2 and minus E2 E1. This is finally resulting into your favorite number. It means the second test is also getting satisfied. Got it? Even if you are not yet convinced, we can have the third test. The E vector and B vector are mutually perpendicular, and the direction of E cross B is always in the direction of the propagation of wave. You remember that? So you once check the data for E vector cross B vector. The direction of propagation of EM wave is always along E vector cross B vector's direction. Okay, can we check the direction of E vector vector cross b vector. Just for sake of simplicity, I'll be again doing cross product between these terms. Pay attention here. E1 I cap cross E2 I cap, that will become 0. So I'm not writing that. E1 I cap cross E1 j cap, that part will remain. So I'm writing it E1 I cap cross E1 j cap. Then E2 j cap and E2 I cap, their cross product will remain something. So E2 j cap cross of E2 I cap. E2 j cap cross E1 j cap. J cap cross j cap becomes 0. So I am not writing that. Let's check these parameters. I cap cross j cap becomes k cap. So here is E1 square k cap. J cap cross I cap, it becomes minus k cap. So here is E2 square and minus k cap. Do you agree? Now, the direction of the propagation of the EM wave is coming along k cap, and actually along the plus z direction we use the unit vector k cap only. Get it? So it was a brilliant question. I hope you understood everything. Note it down, and I urge you to try all these parts once again yourself. Since there was the shortage of the space, so while doing the dot product, I have not written the product of these terms and everything. I hope you understand. Note it down, then we'll take up the next brilliant question. It's a good one, but formula based question, so you may give it a try. I hope you are done with your calculations. So I'm starting the solution here. First of all, we'll find the energy falling on the surface. Okay, light is being incident on the surface. Area is given as 20 centimeter square. So here is the energy falling on the surface. We indicate this by U. U will be equal to the intensity, which is 18 watt per centimeter square, into the given area, which is 20 centimeter square, into the time. Time is 30 minutes, so 30 into 60 seconds. We work in the SI units. See, what is this part? This part is basically intensity into area, and intensity into area gives us the power, and this is the time. Power into time will give you the energy. You understand this thing? We can do the computation and we'll get the value of U, which comes out to be 6.48 into 10 to power 5 joule. Okay. After getting the U, we can find the momentum delivered to the surface. Here is the case of the complete absorption. So I'm writing that data here. For complete absorption, the linear momentum delivered to the surface is equal to, any formula you remember? You can write this as U by C. Okay, P is equal to U by C. If you remember the theory part, we have seen that formula for the complete absorption. U is available 6.48 into 10 to power 5 joule, and the C is speed of light in vacuum, which we can write as 3 into 10 to power 8 meter per second. You can do the calculations yourself and you can verify the data. If we know the P, we can find the average force on the surface. We can use the Newton's second law. Will be equal to P by T. P is 2.16 into 10 to power minus 3 kg meter per second, and the time is 30 minute, which we convert into the second. Okay, doing this computation will get 1.2 into 10 to power minus 6 Newton. An interesting answer. The light incident on this surface is creating a very tiny force, very small force. So usually we don't feel that force, such as right now. The light coming from the light source in this room is falling on my face, on my body, on my hands, everywhere. Do I feel enormous force due to that radiation? No. That force is actually negligible. Do we feel the energy? Yes, you stay in the sunlight for half an hour, you'll feel the energy, you'll feel the heat, but you won't feel the average force due to that sunlight. Okay, so technically the radiation pressure on our body is very small. Now the second part of question is asking, what if this surface is completely reflecting? You remember the theory? If surface is completely reflecting, here comes a factor 2. It means here also we have to multiply a factor 2. So for completely reflecting surface, the average force will be equal to twice of this, which is equal to 2.4 into 10 to power minus 6 Newton. Okay, nice and easy question. You may note it down, then we'll go further. Here is the next question, simple one, formula based. So you should give it a shot, then we'll be simplifying it on the board. I hope you are done with your calculations. Pay attention, I am writing the solution here. We treat this bulb as a point source. Okay, the power of the bulb is given as 100 watt. The bulb will radiate energy in all directions. So in 3 dimension, you can construct a sphere. If this is a bulb point source, it will radiate energy in all directions. The radius of this sphere I consider as R. Here I am trying to obtain the intensity. Okay, formula for the intensity we already know, power divided by area. The question says that only 2.5% of this power is being converted to the electromagnetic waves. So I should write here 100 into 2.5 by 100. This is 2.5% of the 100. Okay, divided by area. This power is being distributed on the surface of a sphere. So area for the surface of the sphere is 4 pi into radius square. Radius is given as 3 meter. So 3 square. Getting it? This will give us the intensity. Intensity will come in the units of watt per meter square. Do the numerical computation. It will be 0.022 watt per meter square. We got the first answer, the intensity at this point. On this entire sphere, the intensity will remain same, and as we go farther away, the intensity will decrease. The electric field and the magnetic field components contribute equally. It means the intensity due to the electric field at point P, if I name this point as P, let's say P we have used for the power, I'll name this point as P star. Okay, will be half of this, so 0.011 watt per meter square. And if you want to find the intensity at point P star due to the magnetic field, then your answer should be 0.011 watt per meter square. Okay, both contribute equally here. Now going further for the next part of the question. Question is asking here, what is the amplitude of the electric field? That's simple actually. For intensity, I know the formula. Intensity is equal to half epsilon naught E naught square and C. Data of intensity is available. I am writing that here. 0.022 is equal to half. What is the data for epsilon naught? 8.85 into 10 to power minus 12. Then this E naught square remaining, and then here comes 3 into 10 to power 8. In this entire calculation, what is unknown? E naught. Do the mathematical calculations. The E naught will come out to be 4.07 volt per meter. Okay. So 3 meter away from this lamp, we have the sufficient amplitude of the electric field. So when you are sitting closer to the lamp, you can read easily. Got it? Now we need to obtain the amplitude of the magnetic field. That can also be done. We remember a formula. E naught by B naught is equal to C. So what is the value of B naught? B naught is equal to E naught by C. Okay. E naught is 4.07. C is 3 into 10 to power 8. Doing this computation, we'll get the strength of the magnetic field, which is 1.4 into 10 to power minus 8 Tesla. Interesting insight. This data is smaller as compared to the magnetic field of the earth, and that is practical thing. When you switch on the study lamp or a bulb, do you feel any magnetic effects around the bulb? The oil pin gets attracted, any iron piece gets attracted? No. Actually, the amplitude of the magnetic field is very small. So you don't feel any magnetic effects. Got it? Another interesting insight. Amplitude of electric field is much greater as compared to the amplitude of the magnetic field. But in the intensity or in the energy density, both components will have the equal contribution. You should note down all these informations. Now it's time to answer the 4 opening questions of this video. The first question was about light installation by the Richard box. The fluorescent lights glow under the high tension power lines. In the entire video, you have learnt a lot of concept. So can you answer it now? Okay, the correct answer is the high tension power lines carry the alternating current. Alternating current means charges are oscillating, and oscillating charges will radiate the electromagnetic waves, and electromagnetic waves carries the energy, momentum. Remember that? So that energy will create a faint glow in the fluorescent light. Understood the answer? The second question was regarding the radars. How the radars come to know about the distance of a plane, about the location, size, shape, all these parameters. Remember the question? Any answer from your side? Okay, the correct answer is the radar sends the electromagnetic waves, and those waves get reflected by the plane. So radar sends the electromagnetic wave, it gets to that particular plane and gets reflected and come back to the radar. This time interval can be measured. Time for going and then time for coming back. Total time interval can be measured. And these EM waves travel with the speed of the light in air. In vacuum, they travel with the speed of light, and almost in air, they travel with the same speed. So you know the time taken, the wave is sent and received back, and you know the speed of the wave. It means you can find what? The distance of the plane. Remember the simple formula, speed is equal to distance upon time. Done? And how the radars come to know about the shape or size of the plane? Different kind of planes will reflect different intensity of the radar waves. Got the idea? Different kind of planes have the different shape, different size. So the reflected intensity will also be different. Radar will measure the reflected intensity, and using that intensity, radar gets the signature of the plane. By the word signature, I mean the shape, size of the plane. Okay. Let me ask you another question. I have two personal planes. This is and this one. It's a fighter jet and it is my personal jet. Can any radar in the world detect these two? Yes or no? What is your opinion? None of the radars in the world can detect these two. Why? Actually, the area is very small. So the reflected intensity will be very small. That much small intensity radar might not observe, radar might not sense. So none of the radars in the world can detect these two. Okay. Then there comes the next question about the TV. In the European countries, in the UK, you need a license to watch the television. Without license, there are fines. So how the inspectors come to know that you are watching a TV without license? The logic is simple. Your TV receives the channels in the form of the electromagnetic signals, and these signals are amplified using a tank circuit inside the TV. Suppose there is a particular frequency F0, you want to watch that channel, then related to that particular frequency, the circuit inside the TV is in resonance, and that resonating circuit is actually using the oscillating charges. Oscillating charges will produce the EM waves, and these radiated EM waves from the TV can be detected by the detector vents, or even there are handheld devices which can detect the radiations coming from the TV, and these devices can even tell that which frequency, means which channel, is being watched. Okay, so when might be outside of your home, or an inspector might be outside of your home and far away from your home. Using the devices, they can detect which channel is being watched. Done. And the last question was about a new technique of the space travel, the solar sail spacecraft. The solar sail spacecraft, I think now you can answer. The material should be highly absorptive or highly reflective. Correct. The simple answer is material should be highly reflective, because if you remember the theory and we did questions, for reflective material, the force is twice as compared to the force due to the absorptive material. Got it? So the solar cells should use a material which is highly reflective. Although we know that the EM waves exert a very tiny force on the surfaces. So propelling a large spacecraft, a heavy spacecraft with this method is presently not at all feasible. Got it? Small grains of the dust or the vapors, they can be propelled using the radiation pressure. In the presence of the sunlight, the comet's tail is visible on the screen. Now, can you tell me where is the sun in this diagram? Actually, due to the radiation pressure of the sun, the comet's tail will always point away from the sun. Whether the comet is approaching or going away from the sun, its tail will always be directed away from the sun, because sun's radiation pressure will vaporize some material in the comet. At these vaporized materials, the gases, they will be pushed away from the sun because of the radiation pressure. Okay, so this is all about this video from my side. Now you will be getting a checkpoint for conceptual practice, and I request you pause there and you try all those questions, and at the end of this video you'll get the answers of all these checkpoints. And if you want me to make video on any other topic, let me know in the comment box. I'll try to bring the best of knowledge for you. Stay awesome. See you again.